Binary iron sulfide as a low-cost and high-performance anode for lithium/sodium-ion batteries. Iron-based sulfides have been deemed as an appealing anode material for lithium-ion batteries, LiBs, and sodium-ion batteries, SiBs, for their high theoretical capacity and low cost. However, their practical application is limited by drastic volume expansion during cycling and low intrinsic electronic conductivity. In this work, we report a FeS2/Fe7S8 RGO composite synthesized via a facile solve other mol method as in LiB/SiB anode. The FeS2/Fe7S8 RGO anode exhibits an excellent Li storage capacity of 514 mAh at 2.0 Ag1 after 3000 cycles and a Na storage capacity of 650 mAh at 0.2 Ag1 after 250 cycles, respectively. The RGO matrix is deemed responsible for providing good electron conduction and alleviating volume expansion during cycling. The electrokinetic analysis confirms a large portion of intercalational pseudocapacitance as a major contribution to the superior rate performance. In situ X-ray diffraction further reveals details of a combined intercalational and conversional Li-ion storage mechanisms in this Fe sulfide-based anode. Finally, density functional theory calculations suggest that there exists a synergistic effect at the hetero-interface between FeS2 and Fe7S8 to promote electrokinetics. Marcasite iron sulfide as a high-capacity electrode material for sodium storage. Abstract. Iron sulfides have attracted significant attention as promising electrode materials for sodium-ion batteries, SiBs, owing to their low electronegativity, high theoretical capacity, and cost-effectiveness. However, the large size of sodium ions generally induces severe volume changes and sluggish sodium kinetics in iron sulfide electrodes, which have prevented their practical application in SiBs. Herein, an orthorhombic marcasite FeS2 was successfully synthesized under solve other mol conditions and subsequently modified using electroconductive carbon. This report is the first to use marcasite FeS2 as an electrode material in Na cells. The FeS2/carbon composite exhibited a high Na storage capacity with stable capacity retention in Na cells, specifically, a discharge capacity of 385 mAh1, over 85% of the initial capacity, was retained after 200 cycles at 100 mAh1. The following related Na storage mechanism was proposed: FeS2 plus 2 Na plus 2 EFES plus Na2S on sodiation, reduction, and this reaction occurs reversibly on desodiation, oxidation. The FeS2 cathode in the Na cells delivered a high energy density of approximately 620 Wh/kg1 even after 200 cycles, which is comparable to that of commercial cathode materials for lithium-ion batteries. Iron sulfide Na2FeS2 as positive electrode material with high capacity and reversibility derived from anion cation redox in all solid-state sodium batteries. Abstract. It is desirable for secondary batteries to have high capacities and long lifetimes. This paper reports the use of Na2FeS2 with a specific structure consisting of edge-shared and chained FeS4 as the host structure and as a high-capacity active electrode material. An all-solid-state sodium cell that uses Na2FeS2 exhibits a high capacity of 320 mAh1, which is close to the theoretical 2-electron reaction capacity of 323 mAh1, and operates reversibly for 300 cycles. The excellent electrochemical properties of all solid-state sodium cells are derived from the anion cation redox and rigid host structure during charging/discharging. In addition to the initial 1-electron reaction of NAxF2, 1x2, activated Fe2 Fe3 redox as the main redox center, the reversible sulfur redox further contributes to the high capacity. Although the additional sulfur redox affects the irreversible crystallographic changes, stable and reversible redox reactions are observed without capacity fading, owing to the local maintenance of the chained FeS4 in the host structure. Sodium iron sulfide Na2FeS2, which combines low-cost elements, is one of the candidates that can meet the high requirements of practical applications. 1. Introduction. Energy storage devices have been regarded as the key to achieving a carbon-neutral society. All solid-state sodium batteries are expected to satisfy the increasing demand for high-energy and large-scale devices, such as mobile and stationary power supplies for smart grid systems. 1 to 3. Sodium is a well-known cost-effective carrier cation because of its abundance in the Earth's crust and widespread distribution. 1. In order to increase the utilization of energy storage devices, more convenient substitutes are needed for other component elements of batteries. Iron sulfides are useful active material candidates owing to their availability and low toxicity. 4 to 8. FeS2 has shown a high capacity of 470 MacG1, derived from the redox reaction of SS2 to S2. Its redox and structural changes have been revealed in detail, and conversion reactions with large rearrangements are often associated with inhomogeneous reactions and degradation. 5. In recent reports, layered iron sulfides such as Li-titanium-1 Sfex2 and Li2FeS2 have also been investigated for use in lithium-ion batteries, in addition to FeS2 as a major active material. 9. 10. Rigid structures such as layered materials are also advantageous for ionic conduction and reversible reactions resulting from topochemical reactions in the host structure. 11. 12. Initial structures consisting of transition metals and sulfur lead to essential improvements by designing the ionic conduction pathway and overcoming structural challenges. Sulfur redox in sulfide active materials via conversion reactions has been positively exploited and reported for Na2S13, 14 and transition metal sulfides such as FeS2, TiS3, and Vs415, 16. Although reversible anionic and cationic redox reactions were recognized as anion-cation redox reactions by Rosell in the 1970s in layered transition metal sulfides such as TiS2, 17. The relationships between the structural evolution and redox species in layered sulfides have been considered in the context of anion-cation redox. 9, 10, 18 to 20. Meanwhile, in transition metal oxides, the relationship between structural evolution and redox species has attracted considerable attention owing to the introduction of additional anionic reactions to achieve a high capacity. However, large voltage hysteresis and significant capacity fading have been reported. 21 to 23. Some researchers have proposed electrochemical reaction mechanisms for producing OO hybridization with octahedral distortion without O2 formation. 23 to 25. One of the solutions to achieve high-capacity active materials with reversibility is the kinetic interruption of OO hybridization through the design of their crystal structures. 26 to 29. In transition metal sulfides, the initial structure is selected for the activation of the anion-cation redox reaction. Topochemical reactions with the remaining host structures are also effective in developing high-capacity active materials with high reversibility. Transition metal sulfides have a possibility to form diverse structures owing to the lower electronegativity of sulfur as a sublattice, thus, stable host structures are available, in addition to the layered materials. In this study, we focus on sodium iron sulfide Na2FeS2 with a specific structure. The host structure is constructed with edge-shared FeS4 tetrahedra as shown in figure 1a30. The chained FeS4 tetrahedral sandwiched Na ion with a parallel orientation resembles a layered structure. We demonstrate the high electrochemical performance of Na2FeS2 in all solid-state batteries with high reversibility. In addition, we evaluate the chemical state and crystal structure of Na2FeS2 during the charge-discharge process and reveal the relationship between the structural evolution and redox reaction with anion-cation redox. In particular, the host structure consisting of chained FeS4 tetrahedra showed elastic recovery, indicating that the active material could withstand long-term cycling. Figure 1. Open in Figure Viewer PowerPoint. A. Refined XRD patterns of Na2FeS2 and a crystal structure in inset. B. Bond valence-based energy mapping at isosurface level of 0.6 eV by Na plus in the crystal structure of Na2FeS2 on 110 and 011 calculated by soft BV. Blue dots ranges are isosurface of sodium ion, meaning that the predicted pathway connecting two distinct crystallographic sites. 2 Results and discussion. Figure 1 shows the initial structure and sodium migration pathway predicted by soft BV31. The X-ray diffraction, XRD, patterns of the synthesized Na2FeS2 were used to refine the structure of Na2FeS2 and Na15FeS2 as the secondary phase, and it was confirmed that the compound was mainly composed of Na2FeS2 with IBAM space groups 32. Table S1, supporting information, lists the detailed refinement parameters. The obtained structure consisted of laminated sodium and the edge-shared and chain-like arranged FeS4 tetrahedra along the C-axis. Additionally, the sodium conduction pathways are shown in Figure 1b by the blue-labeled ISO surfaces, with the possibility of sodium cations, and the pathways connecting two distinct crystallographic sites of sodium ions have 1d directions along FeS4 chains. The electronic and ionic conductivity of Na2FeS2 were also experimentally evaluated by DC polarization using an ionic blocking cell and electronic blocking cell, respectively. Figure S1, supporting information. The electronic conductivity was 1.6 times 10^2 sm1 and the ionic conductivity was 7.0 times 10^7 sm1. A structural analysis showed that the ionic conduction was promoted by the aligned FeS4 sequence, which was similar to a layered structure. Figure 2 shows the electrochemical properties of all solid-state cells that used Na2FeS2 as the active material. First, the redox reactions of Na2FeS2 were evaluated in each state of charge, social, by limiting the upper cutoff voltage to 2.4, 2.6, and 3.0 V in the same cell with Na2FeS2. The lower cutoff voltage was fixed at 0.7 V, and the three operating conditions with the different upper cutoff voltages were denoted as ranges 1, 2 and 3, respectively. Figure 2a shows the reversible charge-discharge curves under each voltage condition, where three distinct curves are observed, and Figure S2, supporting information, shows the results of examinations using other voltage limitations. Figures 2b-d show second galvanostatic intermittent titration technique, GIT, curves at a low current density of 0.013 mA cm2 for cut-off voltages of 2.4, 2.55 and 3.0 V corresponding to ranges 1, 2 and 3, respectively. As shown by the summarized first GIT cycles in Figure S3a, supporting information, the discharge curves were different, while the charge curves were similar at the first charging. A GIT curve with a 2.2 V limit was also measured as a result of observing a potential step at 2.3 V on the first charging, Figure S3b, supporting information. We selected the 2.4 V operation as a representative example because the second cycle curves limited by 2.2 and 2.4 V had similar behaviors, and the capacity for 2.4 V corresponded to the 1.0 Na extraction. When charging using 2.4 V in range 1, a potential plateau was obviously observed at 2.1 V, and during discharging, a potential plateau paired with the charging plateau was observed at 1.8 V. In the GIT curves of range 1, four areas could be roughly distinguished for the potential changes. These included a shallow slope area 1 V, a plateau area at 1.95 V, and deep slopes before and after the plateau. The differences between the open circuit potentials during charging and discharging were within 0.1 V in almost all of the operations, and the redox reactions were symmetric in suppressing voltage hysteresis. In addition, the polarization of the cell was different in each of the four potential areas. The social/depth of discharge, DOD, was dependent on the polarization, and the sodium diffusion in the structure considerably affected the cell polarization. In range 1, the polarization was relatively suppressed during the entire charge-discharge process. This result suggested that the highly diffusive structure remained with the pathway predicted by soft BV. Figure 2. Open in Figure Viewer PowerPoint. Charge-discharge curves of all solid-state cells with NaSN/Na3PS4/Na2FeS2, 38 Wt%, Na3PS4, acetylene black, AB, A, the reaction mechanism evaluation results for Na2FeS2 applying various upper cutoff voltages from 2.4 to 3.0 V to the all-solid state cell. The lower cutoff voltage was fixed at 0.7 V, and the current density was 0.038 mA cm2. Range 1, 2 and 3 indicates the operation with upper cutoff voltages of 2.4, 2.6 and 3.0 V, respectively in B, C, and D. The first Git curves of the all-solid-state cells with NaSN/Na3PS4/Na2FeS2, 38 Wt%, Na3PS4, acetylene black, AB, corresponding to the conditions set for ranges 1, 2, and 3, respectively. Range 2 used 2.55 V as a result of the different polarization of the cells by a low current density of 0.013 mA cm2. When charging to 2.6 V, range 2, a new additional potential plateau at 2.5 V was seen after observing the previous plateau. In contrast, the new plateau was not reversible upon discharge, although the charge and discharge capacities matched. The redox mechanism was altered without the capacities fading. As seen in figure 2c, the corresponding Git curves at 2.55 V confirmed the voltage hysteresis when charging above 2.5 V. The open circuit voltage, OCV, of the plateau was flat 2.4 V during charging. However, slanted potentials from 2.5 to 2.0 V were observed during discharging. The hysteric area was unveiled by extracting over 1 molar desodiation, showing the asymmetric reaction mechanisms with the structural evolution. Figure S2, supporting information, shows charge-discharge curves of the all-solid-state cells applying various cut-off voltages. When the charging progressed in 0.05 V increments from 2.2 to 3.0 V, the plateau 2.5 V gradually expanded, and subsequently the plateau became obscured over 2.7 V. When charging at 3.0 V, range 3, the shapes of the charging curves were different from those at 2.6 V. The first charging curves at 2.4, 2.55 and 3.2 V overlapped until the end of each charge, and the charging process over 2.6 V strongly affected the reaction symmetry of Na2FeS2. Compared to the curve of range 2, the plateau observed at 1.95 V of range 1 was more ambiguous, suggesting that the structure underwent an irreversible change, and was separated by de-insertion above 1.5 mol. A remarkably hysteresis was observed in the Git curve of range 3, and the potential plateaus at 1.95 and 2.5 V were shortened. The first Git charge curves for 3.2 V showed a flat OCV at 2.3 V for 0.21, as shown in figure S3a, supporting information. Thus, it was not possible to separate range 2, which showed the hysteric curves, from range 3, which showed an irreversible change. The Git curve showed a high polarization of greater than 0.2 V when charged to over 2.5 V, which deteriorated from the operation of range 1. The increase in polarization demonstrated high resistance and low sodium diffusivity. After the first charging over 2.526 V, the polarization becomes relatively high, which should be caused by the irreversible changes in the redox reaction and which affects the sodium diffusivity. In summary, the redox mechanism was classified into 3 steps: a symmetric reaction and hysteric reaction by the social in the first charging. The former boundary between range 1 and 2 was determined by the rising of OCV at 1 molar desodiation. However, the latter boundary between ranges 2 and 3 was ambiguous in terms of the OCV. In the potential plateau at 2.5 V, the redox reaction was similar at least in the first charging, thus the two ranges were too difficult to be distinguished. Here, we discuss the two distinct steps denoted as the narrow voltage operation of range 1 at 2.4 V and wide voltage operation of range 3 at 3.2 V, in relation to the crystal structures and chemical states. Figure 3a, B shows the charge/discharge curves under the condition of the sufficient extraction in Na2FeS2 with a low current density of 0.013 mA cm2 at 25 degrees C. Cut-off voltages of 0724 and 0732V were applied to ranges 1 and 3, respectively. The all-solid-state cell with Na2FeS2 showed a high capacity of 170 MacG1 in range 1, corresponding to 1.0 mol Na per Na2FeS2. The all-solid-state cell with Na2FeS2 showed a high capacity of 274 MacG1 in range 3, corresponding to 1.7 mol Na per Na2FeS2. The wide voltage operation was advantageous to the high capacity, although a large voltage hysteresis was observed. After the irreversible changes during the first charging at 3.2 V, the second and third cycles overlapped, with no capacity fading. Figures 3c, d show ex situ XRD patterns of the charged and discharged cells with Na2FeS2, while operating in the selected social and DOD for ranges 1 and 3, respectively. In the lower voltage operation of range 1, all the observed XRD patterns showed that crystalline NAXFS2, 1x2, was obtained. The reaction yield was 0.3 molar electrons, which was equal to Na17FeS2, and the active material turned into Na15FeS2 on the first charging at 1.3 V. After the first charging at 2.4 V, NaFeS2 was observed, and the phase transitioned from Na2FeS2 to NaFeS2 via Na15FeS2 with charging. The reaction yield of sodiation was 1.0 molar, corresponding to the formula composition of NaFeS2. After the discharge, Na2FeS2 and Na15FeS2 were repeatedly observed, and NaFeS2 was confirmed in the second charging. In terms of the crystal structure, a reversible and symmetric reaction was observed in the lower voltage operation of range 1. In contrast, the higher voltage operation in range 3 caused a decline in the crystallinity. After the first charging at 3.2 V, the XRD pattern only showed faint diffraction peaks derived from NaFeS2. During the discharging and next charging, the faint diffraction peaks were not intensified and showed faint changes between Na2FeS2, Na15FeS2 and NaFeS2. In the operations of both ranges 1 and 3, the fully discharged sample showed a residue of the Na15FeS2 phase. This is because the phase transition from Na2FeS2 to Na15FeS2 is supposed to be the earliest process of charging, as indicated by NAXFS2 at 1.1 V in figure S4, supporting information. The capacities of the second and third cycles are also very close to that of the first cycle, although the average structures observed by XRD measurements change drastically. This similarity was due to the same redox species in the first and after second cycle. When the cells were operated at high temperatures, as discussed below, the capacity was consistent with the theoretical capacity, and the difference from the theoretical capacity for room temperature operations shown in figure 3b can be attributed to inadequate utilization of the active materials. As observed in the charge-discharge curves for range 3, the OCV changes were related to the irreversible structure changes. The irreversible changes during the high-voltage operation were discussed in relation to the changes in the redox centers based on the redox models for alkali-rich transition metal oxides. In the iron sulfides, NAXFS2, X1, the contribution of the sulfur increased and was also predicted to affect the structural evolution. Figure 3. Open in Figure Viewer PowerPoint. Charge-discharge curves of all solid-state cells with NaSN/Na3PS4/Na2FeS2 cell during a low-voltage operation, range 1, between 0.7 and 2.4 V, and B, high-voltage operation, range 3, between 0.7 and 3.2 V under 0.013 Ma cm 2 at 25 degrees C. C. Ex situ XRD patterns of the cells with Na2FeS2 at points I, V, on charge/discharge in range 1. The observed points are I, pristine, 2, charged at 1.3 V, 3, charged at 2.4 V, 4, discharged at 0.7 V, and V, secondary charged at 2.4 VD, ex situ XRD patterns of the cells with Na2FeS2 at points 6, 8, on charge/discharge in range 3. The observed points are 6, charged at 3.2 V, 7, discharged at 0.7 V after charging at 3.2 V, and 8, secondary charged at 3.2 V. Figure 4 shows the ex situ, A, 57 Fe Mossbauer spectra, and B, S2P X-ray photoelectron spectra, XPS spectra, of the all solid-state cells with Na2FeS2 after operation. The positive electrodes of the cells were constructed using only the compressed active material Na2FeS2 to ignore the sulfur from the Na3PS4 solid electrolyte. The charge-discharge curves are shown in figure S5, supporting information. Because Na2FeS2 is a mixed ion electron conductor with high ductility, the cells showed reversible capacities of 250 MacG1. The lower capacity originated from the short potential plateau at 2.5 V, which accounted for the lack of ionic diffusivity at the end of charging. The cells showed an initial irreversible capacity of 5%. This was probably due to volumetric changes caused by charging and discharging. Before the charging and discharging denoted as I, pristine, the Mossbauer spectrum showed two distinct doublets with large isomer shift, is, values of 0.52 and 0.36 mm S1, which were indexed to Fe2+. Large quadrupole splitting, QS, values of 0.98 and 1.69 mm S1 clearly suggest that Fe2+ ions reside in tetrahedral sites, which agrees with the XRD result. The Fe2P XPS spectra also showed a main peak at 706.8 eV, which was near the peak derived from the FeS2 standard at 707.1 eV, figure S6a, supporting information. The S2P XPS spectra showed doublet peaks at 159.9 and 161.2 eV indexed to S2P3/2 and S2P1/2, respectively. The chemical state of sulfur was single and highly ionic, resembling that of S2 of Na2S, 159.5 eV. The local polarization showed the ionic bonding of S-Fe and SNA. In addition, the high ionicity was related to the sodium-rich coordination of sulfur in the crystal structure of Na2FeS2. The chemical states of iron and sulfur were regarded as Fe2+ and S2, corresponding to the formal charge of Na2FeS2. Figure 4. Open in Figure Viewer PowerPoint. A. 57 Fe Mossbauer spectra and B. Ex situ XPS S2P spectra of cells with Na2FeS2 at points I, 8, on charge/discharge. The observed points correspond to those in Figure 3. C. Schematic diagrams of the crystal structures and the changes in Na2FeS2, Na15FeS2 and NaFeS2 observed during one electron reaction in range 1, and the predicted structure changes in NaXF2, X1, in oxidation involved with sulfur redox. The green balls and brown tetrahedra with yellow vertices are sodium and FeS4 tetrahedra, respectively. After the first charging of X = 1 at 2.4 V, the Mossbauer spectrum showed a mixed valence of Fe3+ and Fe2+. The fraction of Fe3+ was 65%, and the redox center was mainly Fe2+/Fe3+ in the first 1 molar reaction. In the Fe2P XPS spectra, the peak was obviously shifted from 706.8 to 707.7 eV. The S2P XPS spectra dominantly showed the chemical state indexed to S2 at 160.5 eV. The binding energy was shifted from that of Na2FeS2 in a high energy direction. The shifts showed that the sulfur redox also occurred during the lower voltage operation. As shown in figure S6b, supporting information, the high energy shift in the S2P XPS had already been observed in the cells charged to X = 1.7 by 1.3 V. When charging to X = 1.0, the spectra indexed to S2 at 160.5 eV were mostly unchanged. While the shifted and sulfur oxidation occurred in the initial shallow slope area at 1 V, there was little chemical state change in the sulfur at the potential plateau of 1.95 V. On the first charging to X equals 0.4 at 3.2 V, the Mossbauer spectrum showed two doublets with small s values of 0.31 and 0.19 mm S1, indicating that the iron was fully oxidized to Fe3+. The Fe2p-XPS spectra showed little change. Although the shape of the S2p-XPS spectra was largely unchanged from that of the lower charging, S2 was further shifted toward the high energy side at 160.9 eV. The changes showed that the sulfur redox was activated during the high voltage operation in range 3. According to the stoichiometric calculation for the reacted electrons, the sulfur redox mainly contributed to the reaction over 2.4 V. Under the condition for further dissociation expressed as 6 of figure S6b, supporting information, the S2p spectra was further shifted to the high energy side at 161.4 eV. In the NAXPS2, the sulfur redox caused an increase of the covalency without the SS formation. After discharging, the Mossbauer spectrum showed Fe2+/Fe3+. 23% of the iron did not return to its original oxidation state, which was the result of the irreversible capacities of the cells without solid electrolytes in the positive electrodes. The S2p-XPS spectra showed two peaks at 159.8 eV for fully reduction sulfur and 161.2 eV from the reduction residues of the irreversible capacities. The highly shifted S2p spectra were probably produced by a charge disproportionation in the structure. In the second charging, the tendency was replicated in the S2p shifts toward the high energy side. As shown in figure S6, supporting information, the Fe2p-XPS spectra were indexed to Fe2+ and Fe3+, following the first discharging and second charging, respectively. The charge-discharge curves show that the redox reaction was constant in every cycle after the irreversible changes during the first charging. The Na2FeS2 redox reaction was an anion-cation redox and was significantly different from the pyrite FeS2 redox reaction, which was mostly a result of the sulfur bonding and dissociation in the two-electron reaction. For the cooperation of the iron and sulfur redox tried to mitigate the contribution of the sulfur redox, leading to the suppressed formation of SS bonding, as appears in FeS2. The structural evolution is summarized in figure 5c, which was predicted by the ex situ characterization using XRD, Mossbauer spectroscopy and XPS. In the initial low-voltage operation with X equal 1 in range 1, the obvious phase transitions were depicted as crystalline. The Na15FeS2 and NaFeS2 retained their specific structures with edge-shared FeS4 tetrahedra orientating a chain-like sequence. In the structure of Na15FeS2, the chain-like FeS4 was partially wound. The sulfurs shared between the winding tetrahedra were close to each other. The change in the interaction was related to sulfur oxidization. On the other hand, the NaFeS2 showed straight-chained FeS4 tetrahedra with a structure similar to that of Na2FeS2. In comparison to Na2FeS2, the FeS4 tetrahedra were shrunken by an increase in the covalency of Fe(S) in NaFeS2. The reaction for Na2xFeS2, 1x2, was regarded as an intercalation reaction with the chain-like FeS4 as a host structure. The pseudo-topochemical reaction led to reversible and symmetric changes in the Git curves of range 1. Figure 5. Open in Figure Viewer PowerPoint. A. Cyclability of all solid-state cell with NaSN/Na3PS4/Na2FeS2, 38 Wt%, Na3PS4, UB at 60 degrees C. Charge-discharge curves of the all-solid-state cell using current densities of B, 0.130 Ma cm2 during the initial 15 cycles and C, 0.255 Ma cm2 during the subsequent 300 cycles. When the oxidation of sulfurs progressed in range 3, the Fe(S) bonds had greater covalency. According to the transition metal-oxygen octahedral distortion in the anion redox and observation of the crystallographic changes in Na15FeS2, the shrinking and distortion of the FeS4 tetrahedra with the close approach between sulfurs were related to the sulfur redox, figure S7, supporting information. In a previous report on layered Li2FeS2, sulfur hybridization also caused shrinking and changes in the bond angles of Fe10. The distortion wound the chain-like structure and disrupted the long-range arrangement. However, the Fe coordination was tetrahedral in the Mossbauer spectra and sulfur dimerization was relatively suppressed in the entire reaction. These results insisted that the host structures consisting of the chained FeS4 were mostly remained in the reaction, which attributed to the reversibility of reaction. The different operations in ranges 2 and 3 were attributed to the amount of oxidized sulfur, and irreversible conformational changes are expected when the progress of the oxidation exceeds the threshold. In summary, during the initial 1-electron reaction at 2.4 V in range 1, reversible structural changes occurred under the major Fe redox and minor sulfur redox, while the crystallinity remained. When the dominance of the sulfur redox increased, the chained FeS4 tetrahedra became more waved, and the structure was more disturbed. The underlying mechanisms are very complex in detail, and have been not fully understood. Further intrinsic changes, including reaction mechanisms in each potential region, should be investigated in future works. Figure 5 shows the cyclability of the all-solid-state cell with Na2FeS2 at 60 degrees C. The cell had high cyclabilities with an average Coulombic efficiency of 99.9% for 300 cycles, as shown in Figure 5a. As seen in Figure S8, supporting information, after long-term cycling over 800 cycles, the high discharge capacities remained, although the capacities were unstable because of the reaction between the solid electrolytes and counter-electrodes. The charge-discharge curves of the cell at 0.130 and 0.255 mA/cm2 are shown in Figures 5b, c, respectively. The initial 15 cycles showed a gradually capacity increase as a result of the increased utilization of the active material. Under a high current density as shown in Figure 5c, the shapes of the curves almost overlapped, although the plateau was ambiguous because of the polarization. For 300 cycles, an increase in capacity was observed at the end of charging. According to the GIT analysis, high polarization was observed at the end of charging, indicating that sodium diffusion was relatively slow in this region. Therefore, the increase in the current density from 0.130 to 0.255 mA/cm2 kinetically limited the reversible capacity. During long-term operation, the utilization of active materials was increased by improving the diffusion coefficient at the end of charging and / activation of the solid electrolyte as an electrode active material. After the irreversible changes during the first charging, the charging and discharging reactions remained, showing the stable and reversible redox reaction mechanisms of Na2FeS2. Figure S9, supporting information, shows the S2p-XPS spectra of the cells after 50 cycles. The binding energy of the S2p peaks effectively corresponds to that of the first cycle during the charge and discharge. The sulfur redox in Na2FeS2 could occur in the all-solid-state cells. Although the anion redox of sulfur affected the irreversible structural changes, the reversibility of the capacities was negligible. 3. Conclusion. The sodium iron sulfide Na2FeS2 was used as the active material in an all-solid-state sodium battery. The cells with Na2FeS2 showed different redox reactions, depending on the social, which were regarded as ranges 1, 2 and 3. Regardless of the operating range, the redox reaction progressed without having the capacity fade. In range 1, Na2FeS2 exhibited 170 MacG1, corresponding to a 1-electron reaction. The Fe2+/Fe3+ redox mainly contributed to the reaction, along with the minor sulfur redox, and a reversible reaction as a pseudo-topochemical intercalation reaction was observed with the remaining specific chained FeS4 in the crystal structure. In range 3, Na2FeS2 exhibited a high capacity of 320 MacG1, corresponding to a 2-electron reaction, with high reversibility for 300 cycles at 60 degrees C. In range 3, the chemical states of Fe and S also changed, with no distinct SS bonding. Thus, the contribution of the sulfur redox increased for more than a 1-electron reaction, according to the stoichiometric presumption. Although the sulfur redox was related to the FeS4 tetrahedra shrinking and distorting, which caused waving in the chained FeS4 and the decline of the crystal symmetry, the host structure with the specific FeS4 arrangement remained. The sulfur redox did not directly lead to cycle degradation, and powerfully assisted the increase of reversible capacity. Na2FeS2, which combines low-cost elements, meets the high capacity and reversibility requirements needed for practical applications. Electrode active material systems based on Na2FeS2 with novel structures, in which anion-cation redox occurs in concert, are expected to contribute to further popularization. For experimental section. All of the procedures were conducted under dry AR except for the heat treatment of Na2FeS2. Material synthesis. The iron sulfide Na2FeS2 and Na15FeS2 were produced using heat treatment and subsequent quenching. Each stoichiometric mixture of Na2S, Nagaoco Limited, 99.1%, Fe, Cogendochemistry, 99.9%, and S, Cogendochemistry, 99.99%, as the starting materials was mixed in an agate mortar. The mixtures were placed into carbon crucibles and sealed in quartz tubes under vacuum. The sealed samples were preheated at 300 degrees C for 1.5 H. After slowly cooling, the samples were heated at 700 degrees C for 5 H and quenched in ice water. Na3PS4 was used as a solid electrolyte for electronic blocking and as a separator. It was prepared using a mechanochemical process and subsequent heat treatment. Following a previous report, 33 Na15SN4 was used as a negative electrode. It was prepared by mechanochemical alloying with Cation black as an electronic conductive additive. 34. Electrochemical characterization. DC polarization was conducted to determine the electronic and ionic conductivities of the ion electron conductors. 35. To evaluate the electronic conductivities, the tri-layered pellets of stainless steel/active material/stainless steel were constructed as ionic blocking cells. The active material layer consisted only of Na2FeS2 powder compressed at 360 MPa. To evaluate the ionic conductivities, pellets with 5 layers, Na15SN4/Na3PS4/active material/Na3PS4/Na15SN4, were constructed as electronic blocking cells. The laminated pellets were compressed at 360 MPa. The DC current operation of the ionic or electronic blocking cells was conducted under the potentiostatic conditions of 0.1, 0.3, and 0.5 V for 120 S or 2 H, respectively. The all-solid-state cells consisted of tri-layer pellets, Na15SN4/Na3PS4/positive electrode, for electrochemical characterizations. The positive electrodes were composites of Na2FeS2, 37.7 Wt%, Na3PS4, 56.6 Wt%, and acetylene black, 5.7 Wt%, mixed in an agate mortar. The pellets were compressed at 360 MPa. To suppress the effect of Na3PS4 on the S2P-XPS spectra, positive electrodes that consisted only of Na2FeS2 as an active material were used for the ex situ XPS measurement cells. The galvanostatic intermittent titration technique was used for measurements at 0.013 μ/cm2 with a relaxation time of 20 H. All of the electrochemical characterizations were conducted using a galvano/potentiostat, VMP, 3, biologic. Material characterization. Characterizations were conducted to evaluate the prepared, charged, and discharged NAXFS2, 02.0. Powder XRD patterns were obtained using a diffractometer, SmartLab, Rigaku, with cubic K radiation, equal 1.54056 times 1010 m. The crystal structures were depicted using the Vesta software 36. The BVS for the Na atoms in the unit cells of Na2FeS2 was calculated using soft BV31 to predict the diffusion pathway. The chemical states of the obtained samples were analyzed by 57Fe Mossbauer spectroscopy and XPS. 57Fe Mossbauer spectroscopy was conducted using a topologic system incorporated spectrometer with a 57CO ray source, calibrated with Fe as a standard. The model fitting was performed with MOSWIN 3.0 software. XPS was conducted using a monochromate small spot XPS system, K-alpha, Thermo Fisher Scientific, with a monochromatic alkali light source, 1486.6 eV. The binding energy was calibrated by the C1s peak of adventitious carbon at 284.7 eV, and the Na1s peak interaction with sulfur at 1070.6 eV. FeS2, Sigma Aldrich, 99.9%, was used as a reference. Acknowledgements. This work was supported by JSPSKAKENHI grant numbers 18H05255, 19H05812, 20K05688, 20J23722, and 21H04701.